Hello students, myself Muthura JMP, working as assistant professor in the Department of Mechanical Engineering at Vidyavardhaka College of Engineering, Mysuru 2. Now I will explain you people about the introduction to heat transfer, heat exchangers and logarithmic mean temperature difference for parallel flow heat exchanger. The derivation I will do. What do you mean by the heat exchanger? A device which transfers the heat from one fluid to the another fluid, it is so called as heat exchanger. Hot fluid to cold fluid. The fluid in the two phases, gas and a liquid phase. In the gas, you have an example of exhaust gas from boiler, oil, water, and etc. Here there will be the solid material in between the gas and then liquid, therefore it will be transferred between the hot fluid and then cold fluid. This is the typical picture of the heat exchanger. Hot fluid will be enters with the temperature THI, hot fluid inlet, and then it will be exit at TH0 as the temperature TH0. Cold fluid will be comes like this and then it will be exit like this. We shall write the temperature TH1, TH2, TC1, TC2. Therefore, parallel flow of the heat will be like this. Parallel flow will be like this. Therefore, both hot fluid and then cold fluid are flowing parallelly. That's why it is so called as parallel flow. Sketch for the parallel flow heat exchanger, it is like this. Note on the sketch, very important, where you have the temperature TH1, this is supposed to be the TH2, this is TC1, and then this is supposed to be the TC2. The sketch is shown is the counter flow heat exchanger. It can be like this or it can have the sketch like this also. Okay, counter flow heat exchanger. Note on the sketch. Here what will happen? Hot fluid is flowing in one direction, cold fluid is flowing in another direction. This is the hot fluid TH and then cold fluid TC. Therefore it is flowing in the ulta direction. Therefore the mass flow rate of the hot fluid, let it be MH, and then mass flow rate of the cold fluid, let it be, and it is having the specific heat capacity CPC, and then this is supposed to be the CPH. Therefore the specific heat capacity of the hot fluid, it is equal to mass of the hot fluid into Cp of the hot fluid. Therefore Cc is equal to Mc into Cpc. This is the specific heat. Mass flow rate of the hot fluid, it is given by kg per second, joules per kg. Therefore kg will get cancelled, kg joules per kg Kelvin, then it is supposed to be joules per kg will get cancelled, second will remain, joules per second Kelvin is the specific heat capacity unit. This is for counter flow. This is another sketch for the heat exchanger, which is shell and tube heat exchangers. Number of shells will be there inside the, number of tubes will be there inside the shell. The shell will be like this. This will be the shell. So number of tubes will be there here. And then hot fluid will be comes here and then cold fluid will flow in another direction. Then in between this you will have the baffle plates. These baffle plates are there to support the tube inside the shell. This is another example of cross flow arrangement, both fluid mixed and unmixed. This is the typical sketch in the compressor, evaporator, condenser and expansion valve, which is comes in your refrigeration. Okay, here what will happens, the compressor, the fluid will comes with the, it is H1, H2, it is in this direction. So in the evaporator it absorbs the heat energy from the hot fluid and then make into the cold fluid, then refrigerant will be get evaporated and given to the compressor. After it is compression, it is come to the condenser, where it is gives off its heat energy to the atmosphere or ambient condition, and then it will comes to the expansion well. In the thermal expansion well, it is expanded to the low temperature and low pressure refrigerant, which is very cold. When it is come in contact with the another fluid, then it will be get evaporated and then becomes vapor refrigerant given to the compressor, where it is VCR. These are the typical heat exchangers that you can see in your refrigerator. This is another kind of the heat exchanger. This is the heat exchanger. This is the heat exchanger which is usually used in the air preheater of the boiler. Air preheater of boiler. Hot flue gases will comes like this, and then it is flows in the number of tubes. Cold fluid will be gives here, and then when it is flows like this, and then it absorbs the heat energy and comes back as the hot fluid. What do you understand from the heat capacity? The product of mass flow rate and the specific heat of the fluid, it is given as the heat capacity. Now see to the parallel flow heat exchanger sketch. Now you have the overall heat transfer coefficient. You know that amount of heat energy transfer it is equal to U into K A delta T. You can write for the tube Q is equal to delta T divided by ln of R2 by R1 into 2 pi Lk. Therefore, R thermal resistance it is equal to ln of R2 by R1 divided by 2 pi L into K. This is the thermal resistance. Therefore, your overall heat transfer coefficient it is equal to U. It is equal. Suppose it is having the internally Hi, externally H0. In between you have R1, R2. Therefore, overall heat transfer coefficient we shall write 1 divided by Hi plus ln of R2 divided by R1 divided by 2 pi Lk plus 1 divided by H0 plus fouling factor. Fouling factor, if it is having the fouling, what do you mean by the fouling? Undesired deposits inside the heat exchanger, something that is what we so called as the fouling factor. Consider in the fouling factor, like this is the fouling factor, fouling due to the undesired material there here, and then here also undesired material you can observe here. Therefore this can be shown say as the fouling factor. Therefore U is equal to 1 upon Hi plus 1 upon H0 plus ln of R2 divided by R1. This is the resistance caused by the pipe. Here solid material will be there. Okay, this is solid material. 2 pi Lk, where L is length of the pipe and then K is the thermal conductivity of the pipe, plus fouling factor. If it is having here both the things you can write fouling as the fouling factor. The sketch for temperature change in the parallel flow heat exchanger. Hot fluid will comes like this TH1 and then exit as the TH2. The cold fluid will comes as the TC1 and exit as the TC2. Therefore, we have the temperature difference. We can write this one as the theta 1. Keep in your mind. This one will be the theta 2. And another thing you can observe here that this is the maximum temperature difference you can observe in the heat exchanger. TH1 minus TC1. T maximum temperature difference it is equal to TH1 minus TC1. Even in the counterflow heat exchanger also, that I will show in the next slide. Theta 1, theta 2 and then delta theta 1 THI minus TCI, this one. Therefore, this is what I so called as the maximum temperature T max. Note down, this is very important thing. Theta 1 is equal to THI minus TCI. Theta 2 is equal to TH2 minus TC2. This is TH2, TC2, TC1, TC, TH1, TC1. HI, 1 I means inlet, 1 means inlet. That you want to know. Cold fluid temperature will rise like this. You can observe here. Okay. CH is equal to MH into CPH. CC is equal to MC into CPC. Compare the value of CH and CC. If the value of CH is less than CH, then CH is equal to C minimum. That we have to consider as the C minimum, or this CC will be the C minimum. This is very important consideration before you starting the problem. Next, heat loss by the hot fluid due to the travel of the distance dx. It is equal to heat gain by the cold fluid due to travel of the dtx. dq is equal to ch of change in the temperature of hot fluid minus cc into change in the temperature of cold fluid. It is equal to overall heat transfer coefficient to the area, small area, into th minus tc. Note down this. Ch is equal to u dA theta. Therefore this one you can write like this, d theta. This one you can write down, and then here minus u dA theta, it is common, integrate on both sides, so you can write like this. Not on all this, ln of integration, then it will be theta, ln of theta, if you apply the limits, theta 2 by theta 1 is equal to ua into this one, dA means you will write as the a area, q is equal to ch into dh, 1 divided by ch is equal to dh divided by q, 1 upon cac is equal to dtc divided by this one. You can rearrange the equation, you will get this one to put here. Put the values of ch and c in the equation, put here in the fourth equation. You can take it outside. Then thi minus tci means theta 1, this one will be the theta 2. Therefore q is equal to ua into theta 1 minus theta 2 divided by ln of theta divided by theta 1. This is the term what we so called as the logarithmic mean temperature difference. The LMTD is equal to theta 1 minus theta 2 divided by ln of theta 1 divided by theta 2. The overall heat transfer coefficient, it is equal to watt per meter square Kelvin. These are the very important steps in your LMTD derivation. LMTD derivation of parallel flow heat exchanger. Counter flow heat exchanger, as usual you write down variation of temperature, it will be like this, theta 1, theta 2, TH0, TH0, TC0. Here theta 1, theta 2. And also you see here, this is THI, TH0. See, also you see here THI, TH0. The maximum temperature is this. This is the maximum temperature. Delta T max is equal to THI minus TCI. Thank you one and all.